This call is now being recorded.
So, I want us to finish off the electric field, right? So, we've already spoken about the electric force, the electrostatic force, and yeah, and everything about it basically. So, now the electric field is actually where the electric force starts, right? The reason an object or a charged object experiences an electrostatic force is due to the existence of an electric field. So with electric field, there are usually two definitions. One, it's electric field, and two is electric field at a point. All right, so we do this. We say, let me do electric field right? So an electric field is basically defined as just a region of space in which an electric charge will experience a force. Right? So simple region of space, an electric charge will experience a force. So what happens is if you take an electric charge and you put it in that or within that region of space, it'll experience a force due to the existence of the electric field. Right. So the direction of the field at a point, usually we say it is the direction in which a positive test charge would move if placed at that point. So we can say, let me just write it. The region of space in which electric charge will experience a force right? So now the direction of the field at a point in the space is the direction in which a positive test charge would have moved if placed at that point. I'll show you what that means. Right, so you should have seen something like this. Say you have a positive charged particle. Could be a sphere or it could be a point charge. So usually it'll have lines like this. These are called electric field lines. Okay, let me draw all of them. No, they shouldn't cross the circle, and the lines themselves shouldn't cross one another. That's one thing. It's very important. Okay, if you get something like this, or a positive charge, you would get that the lines are pointing out. So these lines, all of them, that's what we call an electric field. Right, all these lines combined are called an electric field. Each line is called an electric field line. Right, so that's what an electric field looks like. And then usually you would find that for a negative charged particle, instead of going out, these lines, okay, they look funny now. Instead of going out, These lines go in. Just gonna draw as many as possible. Looks like the sun. So instead of going out, they are going in like this. That's the negatively charged particle. So we'll come back to this. Now, let's finish off the definition of the electric field. We said it's a region of space in which an electric charge will experience a force. Wait, let me. So in this space, because this is all the space, let's mark the space. This is all the space, all of this. So what this definition is saying is if I take an electric charge and I put it within this space, say I put it here or I put it there, or I put it wherever, really, it doesn't matter, but within this space, right? That charge, let's say maybe it's plus or minus Q. Let's say this is plus Q, this is minus Q. That charge will experience a force, and we call that force the electrostatic force. We've already covered what an electrostatic force is, what it looks like, and how to calculate it. So the reason an electrostatic force exists is because of this very concept of an electric field. So an electric field covers a certain region of space, and if by any means you introduce a charge within that space, that charge will experience a force. It's the same as if you've seen a flame, right? A flame usually has the center. Let's say this is the flame, the center, right? And then it radiates heat to its surroundings. So if you are close enough to the flame, you will feel the heat, right? It's the same with electric field. The electric field is what you would call the region of space that will feel hot due to the existence of a flame at a center or at a distance away. Right. So that's the same concept, or it's a similar the example actually would work in this case. Right. So same thing if you've seen in movies, if there's an explosion and the guys are too close to it, they start flying, right? They're experiencing a force because of an explosion. It's the same thing with an electric field. It has a region of space that it covers, and if you come and you introduce a charge into that space, that charge will experience a force, and the force we call it an electrostatic force. And we've already talked about this, and we know what it is. Right. So let me write. Let's write. I want to talk about the direction. So we're saying the direction of the field at a point, right? Let's do this at a point in space. Is the direction in which a positive test charge would move if placed at that point. Right. So what does all of this mean? Say, e.g., if you have a positively charged sphere, right, and it has field lines, You know that for a positively charged sphere or point charge, the field lines have arrows pointing away from the center, like this. The arrows are pointing away, like this. However, for a negatively charged one, they are pointing towards. But for this example, so what happens is, what that definition is saying is, in this region of space, say this is our region of space. It's basically to the ends of the field lines. So if right now we introduce a test charge, here, say this is plus, rather, let's say we want, let me see. So at a point in space, let's say we want to understand the direction of the field at this point, somewhere here. Right. So what this is saying is the direction of the field at that point will be in the direction in which a positive test charge would have moved if placed at that point. So the direction in which the positive test charge would move is dependent on the direction of the field lines, or rather on the charge at the center. So this is the charge at the center, this one. It's positively charged, this sphere. So at this point, we just imagine that we are putting something, a positive Q. Now, we know that like charges repel. So if that's the case, the direction of the field lines at point P, let's call this point P, oh, that's fine. So imagine that this point in space, point P, is a positive charge, right? Even if the field was from a negatively charged particle, we always imagine that the point in space in this region of space is a positive point charge. Right, that's what we imagine. Now we want to understand that if I stand at that point, where will the field or the direction of the electric field be going? To get that, we want to understand So where will this point be going? Point P. We know that point P, because it's positive, and also the field that is being generated is generated from a positively charged sphere. So these are like charges. So therefore, there will be repulsion. What that means is point P will be pushed to the because like charges repel. That's why point P will be pushed to the right. As a result, the direction of the electric field at point P will be to the right. Right. And understand that the opposite would be true if the electric field was being generated by a negatively charged sphere or a point charge. Right. So we'll say so if this guy, if this was negative instead of being positive, what would have happened instead? Point P was going to be drawn towards it, right? As a result, point P was going to be moving to the left. And therefore, the direction of the field at point P would have been to the left. So that is applicable to any region of space, any point along this region of space. We could have placed it here, we could have placed it there, we could have placed it anywhere, basically, right, along this space. We would think of it like that. We would imagine that that point is a positive charged particle or is a positive test charge, and therefore we would want to know where is that point going to move. Right, so that's it. And then now there's another definition. Electric field at a point. Sorry, not electric field at a point, electric field strength at a point. This is another definition that you must know. They may seem similar, but they are slightly different. That's why it's important to mention this distinct difference. So when we talk about the field strength as a point, we're talking about how strong is the electrostatic force that will be experienced by a charged object if it was placed at that point. So coming back to this example, imagine I place a charged object at point P. How strong will the electrostatic force experienced by that object? How strong will that electrostatic force be? Right. So that's what we mean by electrostatic field strength at a point. So what usually happens with electric field is the further you move away from the center, which is where the charge is located, the decrease or the lesser the electric field strength. And the closer you move towards the center, the increase or the higher the electric field strength. So for instance, if I take another point and I put it here, let's say I call it point B, somewhere here, point B will experience a higher electric field strength than point P because point B is more closer towards the center. So that's one thing you must understand. So that's what this definition is trying to explain in a nutshell. So basically, it says it is just the electrostatic force experienced per unit positive charge placed at that point, right? That's what it is. And usually it is given as E F over Q, where E is the electric field, F is the electrostatic force, and Q is the electric charge. Right, so what does it mean? Let me take this guy. Right, so imagine this is point P, and then let me add point the point I'm trying to make is that point A So the reason for this is that A is a lot more closer. It's basically what I've been saying. It's a lot more closer to the charge than B. So that's why A will experience a higher electrostatic force, because at A, it'll experience a higher electric field and therefore a higher electrostatic force. So that is typically what happens. So what we also end up doing is sometimes we want to know, we place a charge at point A and we want to know that how much we imagine there's a charge at point A and we want to know how much electric field does that charge experience. So that's one thing. And we use these formulas that I've already this formula already listed here to actually determine the electric field at a point or at a distance away from the charged particle. The charged particle is a plus or is a positively charged particle in this case, or in this example. It can be negative, by the way. It doesn't always have to be positive. That's all there is to it. So that is one thing you must understand about the electric field. So electric field strength at a point, then we have just the electric field, the definition of an electric field. Now, so with electric field, you must understand that all charged particles have some form of an electric field around them. So the electric field of positively charged objects and the electric field of negatively charged object is not the same. Let's draw it. If it's positive, the lines will be going out. I mean, the arrows will be going out. While if it's negative, they will be coming in. And with drawing the electric field lines, they must never cross the circle. So what I mean by that is they must not go through this perimeter of the circle. It shouldn't go through like this. That's not allowed. Right, so they should only touch the circle, not penetrate it. For negatively charged ones, the arrows are usually coming in. I like to imagine it as it's throwing in whatever is within this electric field. It wants to pull it to its center, while the positively charged one is trying to push away whatever is closer to it, right? Well, that's if you are drawing them individually, but once you're drawing them as a unit, you obviously have to think, is it like charges or is it unlike charges? So this is for positively charged objects. Okay. And then these field lines, the lines must never touch each other. And then penetrate. That is very wrong. So whenever you draw your field lines, they must not cross or penetrate the circle, and they must never cross one another. Right? That's one thing about field lines. Very important. Right. So what then happens is we want to understand the field line patterns or the interaction between these charged objects, right? Remember, all charged objects will naturally have an electric field around them. So what if you bring multiple charged objects next to each other? What then happens in their field lines or to their field lines rather? So that's one thing as well that you must know. So the first one we'll look at is, imagine we have um, electric field lines around two like charges. Like charges. So we'll say maybe these ones are both positive. Right, so Let's see what they will look like. So this is how they would look like. Right. If you check here, the field lines, they never cross one another. Never. Right. The rules are the same. And then one thing you must know is you must know how to sketch this diagram. Right. It's very important for your learning. And also in the exam, they will want you in one way or another to sketch this diagram. So you must know it. It's very important. So this is an example of electric field lines around two light charges and how they actually would look like. So it's basically the electric fields of these two objects interacting with one another. So in this case, it is repulsion because these are two light charges. So what will happen here is repulsion. This is a pattern for repulsion. Now, imagine the negative ones again. Doesn't matter whether it's negative or positive, repulsion still holds. If it's like charges, it'll just be repulsion. Right. So that is repulsion, and then the field pattern for repulsion would look like that. Let's see. Image. And then done. So whether it's both positive or both negative, if it's like charges, you will experience repulsion. Now the only difference here is for the positive ones, naturally a positively charged sphere or particle or point charge or whatever really, the arrows are going outwards. Right, while for the negatively charged guys, the arrows are going inwards, as you can see here. These arrows are going inwards. So that's one thing you should know. But other than that, the structure or the schematic is rather, it has the same profile. So in this case, they are all going out. Right. That's one difference. And then lastly, you would want to know the electric field lines between unlike charges. So let me get my image. So as you can see, This is what you would call attraction. Because for unlike charges, we experience attraction and not repulsion like in the like charges. So if you check the field lines, it's as if they are connecting one another, right? So the positively charged sphere or particle or whatever, right? It has field lines or arrows that are pointing away, while this one, the negatively charged one, it's as if it's accepting or welcoming those arrows from the positively charged particle. So that's one way to think about it. But in essence, you must know how to draw or sketch this schematic, right? That's pretty much it. So let me just a quick note. You must know how to sketch these electric field lines. That's what I want to say. Very important. They will be in your exam in one way or another. Right. So that's all there is to know about the electric field. So there's nothing more or nothing less. Let's see if we can cover. Say we are told to calculate the force experienced by an electron at a point. Right. Okay, let's write the whole thing. E right. Say you are given this problem and you want to calculate the force experienced by an electron at a point in an electric field where the electric field strength is 4,500 newtons per coulomb to the right. So now, how you would find this is quite straightforward actually. We know that if we want to find the electric force experienced by an electron or whatever charge at a point, we can use E is equals to FQ, right? Obviously, one might be thinking we could have used this formula, but the issue with that is we don't know R. We don't know how far it is from the center or from whatever charge is generating the electric field. So we, however, know the electric field strength, which is this guy, and we know the charge because the charge of an electron, we can, it's a constant, I think it's 1.6, right? But it should be negative. Let's see, of an electron. Right. So we know Q is usually 1.6 times, you can say 1.60 times 10 coulombs. Right, so that's the charge of an electron. So however, when we substitute on the equation, we do not include the sign. So say therefore E, we know that E is 4,500. F over it's very important, that one. We do not include the negative sign. Even when we calculate the electrostatic force, right? So then from here, you can find what F is. F is, Kuku, what is F when you punch your calculator? Let me punch mine. Minus 19. Cuckoo, what answer are you getting? Mm. Remember, force is in newtons. So this is how much force the electron would experience. The reason we're saying it's left is because we know that if there's an electric field that is being generated to the right, we know that it is usually for the positive charge. So if we place an electron at that point, there will be an attraction. So the electron will want to move towards the charge itself. That's why we say the force will be to the left. It's a force of attraction. Right. And then let us try another example. Let's say we are asked to find the field strength. Right. At a point in an electric field where a charged particle of maybe 4 nanocoulombs, or say, I don't know, 4.2. We are given a scenario like this, and we are required to calculate the field strength at a point in an electric field where a charged particle of plus 5 nanocoulombs experiences a force of 0.07 newtons downwards. Right. So this is as simple as saying E is equals to F over Q. And we know we've been given F to be 0.07 and our Q is 5 times 10 to the power minus 6. If you remember, not 6, sorry, 9. Nanocoulombs means to the power minus 9. Then from here, you can find your answer. Let me use my calculator. Let us see. With 0.07 divided by 5 to the power minus 9 would give us 14 times 10 to the power 6 newtons per coulomb. So that is the electric field. But then you have to decide the direction of the electric field at that particular point. So unfortunately, in this case, we're not told, is it a positive electric field or is it a negative electric field? But we can say if the force is downwards, it means likely the electric field is also downwards. The reason we're saying that is because if you think about it, if let's assume whatever was generating the electric field is actually something like this, a positively charged particle, right? And then we put plus 5 here, or it says downwards, but imagine this thing is down, and then the force experienced by this thing is downward. It would make sense in that regard, but if it was negative, and there's a large charge here, it wouldn't make sense for it to go downwards. It would instead experience a force upwards. That's why we're assuming that the direction is downwards. Right. So now let's do another question. We can actually do one that is more interesting. Let's see. Which is right. Let's do this one. Say this is our example 3. The jump is quite interesting. Reason for this is electric field almost resembles electrostatic force, so there's no need to keep doing straightforward examples. Let's just do this one. Example 3. Right, so now imagine we have this scenario right here. So we are told that we have 2 point charges and they form a right angle triangle with the point A at the origin, right? Now point A is at the origin, and then their charges are Q2 is equals to that, and Q3 is equals to 3 nanocoulombs minus 3. The distance between A and Q2 is 5 times 10. Okay, we're given that. It's in the diagram. Now we are asked, what is the net electric field measured at point A from the 2 charges if they are arranged as shown? Right. So the best way to do this is to split this scenario. We know that at point A, we have 2 contributions, a contribution from Q2 and a contribution from Q3. So let's start with Q3. Let's call it E1. Let's say this is the electric field strength at A to Q3. So we can call it E1, call it E3 is fine. In this case, we can use this formula because we have the distances and we're also given the charges. So we can say KQ over the squared distance. So now we want to find our force. Say 9 to the power 9 times 3 minus 9 divided by 0.03 squared. The answer is 30,000 newtons per coulomb. Right, we don't care about the direction now because this is not the net force yet, the net electric field, sorry, yet. So we will only mention the direction on the last one. But nonetheless, actually, no, we should mention it. So if we look point A, we imagine point A being a positive test charge, right? Point A being a positive test charge would actually be attracted to Q3 because unlike charges attract. So therefore, it would be upwards. And then let's do electric field at point A, but now due to the charge Q2. Right, you would say same thing, E2 KQ2 over R squared, 9 times 10 to the power 9. Q2 now is 6, right? And then divide by 0.05 all squared. So what's our answer? Let's check. We say 9 times 6 to the power minus 9. And then we divide that by 0.05 squared. So that is 21,000. Is it 600 newtons per coulomb? Right. So we also imagine the same thing. Point A, imagine point A is a positive point charge. Will it be attracted or repelled by Q2? It will be repelled. So when it's repelled, it will move to the left. So we'll say left. Now let's find inlet. Therefore, inlet feature. So what will happen here is, let's call this point A. Let's find 66. Black. Imagine this is point A. So at point A, you will get one to the left, which is E2, and you get another one to the upward direction, which is E1. No, not E1, sorry, E3. Then remember, once you have components like this, the only way to find the resultant is not simply adding. You have to take Pythagoras theorem. Therefore, inlet would be going like that, because actually it should go, so that's where inlet would be going. Right. Therefore, from this, you also get theta. Theta is the direction of inlet. The reason we can't simply say left or right is because now the resultant net electric field is a diagonal type, or is a 2D vector. So the only way to specify the direction of a 2D vector is to use an angle, right? Because it's not only falling in one axis, it's now falling on two axes. So we use inlet will be a square root of E2 squared plus E3 squared, which is 21,600 plus 30,000. That's your final answer right there. And then now to find the theta, theta would simply be opposite, which is E3, over adjacent, which is E2. Therefore, theta is tan. E3 is 30,000. While E2 is 21,600. Right. So let's find these answers. I just wrote equal signs only. So if you say the square root, let's do this, square root of 21,600 all squared thousand six hundred squared, right, plus 30,000 squared. You would find the resultant to be 39,600, 39,000, no, 36,967.01 newtons per coulomb. Right, then now you say the tan, delete, tan of 30,000 over 21,600 is actually 54.25 degrees. Right, so that will be your final answer. So I want you to note something. Since the resultant net force is a 2D vector, we use angle to specify its direction. If the resultant is a 2D vector, like in this case, we use theta to specify its direction. But if it was a 1D vector, we would just say left or right or up or down. Right, so yeah, that's it for this lesson on electric fields. Remember, electric field, there's an electric field at a point. The closer an object is, or the closer a charged object is to the center of whatever is generating that electric field, the higher the force that it will experience. And the furthest away it is from that point, the lower the electrostatic force that it will experience. So electrostatic force is dependent on that distance, which is this r squared. So there's an element on inverse proportionality. Yes. All right. That is it for now.